the things that's very interesting, and one of the reasons we're doing this tour and trying to connect with you, actually comes out of, if you look at fire or disaster incident command, there are different theories of command. Basically three. You can have a very simple incident where a hierarchical command type is very appropriate. Now in the case of climate change, it's a problem that human beings have no history on. We can't look back to someone 300 years ago that, wow, they did a great job, they had very limited resources, they had the appropriate command approach. But as it turns out, what we do know from incident command theory, that if we have a complex incident, which we have little history on, the command type that's most suitable is called swarming. And swarming, it's very interesting. I'll read you some of these attributes. With swarming, our technique, the degree of specialization is minimized, structure is minimized, but the degree of redundancy is maximized. Degree of standardization is minimized. The degree of participation, this is the most important thing, is maximum, meaning the whole population, our entire team, would be participating. Professional knowledge is broad but average, and the width and depth of incident experience is broad but only average. So in the case, bring this back to climate change, we don't, at least in this country, we don't have a federal government that's very engaged. We don't have a hierarchical leadership path. And particularly because the problem is complex and we have no history as humans, as we start learning about this swarming command theory, it's very interesting because you have kind of autonomous groups that are very empowered, that are working together and sharing their insights and successes. And that brings us back to today, why we're here. So we hope to share the details of this project to kind of give you the takeaway at the end of let's go do it. But there's three parts to that, showing that we have solutions that work, and how those solutions can provide an opportunity for leadership, and ultimately kind of leave us with a sense of hope rather than a sense of sort of disempowerment and paralyzation, which we kind of encounter that with not just climate change, but a lot of things going on right now in the UK, in the United States. So back to that, solutions, leadership, and hope. I'm going to talk about some of the technical parts. Why does Passive House work? Why is it important? So, if we want to get ourselves out of this pickle, we need to create structures that are so efficient and use so little energy that they actually can be power generation plants to charge our electric vehicles. Because we know as human beings in the first world, we sort of have three buckets of energy consumption. There's flying in jet aircraft, there's traveling in surface vehicles and the fuels that they utilize for that travel, and there's building occupancy. Now, the beauty of it is we have a technology today that will reduce the amount of energy a building consumes by 80%, which is radical, which when I heard about it first, I didn't really believe it. But the more I studied the history of buildings, the science of it, I realized, yes, it is true that we've been completely, if you'll excuse the term, intellectual midgets when it comes to the technologies that we put in place for our buildings. And once we become very savvy about that, we actually can create buildings. As we have with this one, it's significant because it was a 100-year-old building when we retrofitted it and got down to 1/5 or an 80% reduction in energy. So our rooftop area, when we put solar electric on it, will charge 2 electric vehicles. So in fact, just to give you a sense, the average daily energy consumption of this home is on the order of 8 kilowatt hours. Tesla's new Powerwall 2 offering would power this house with the available energy for nearly 2 days with just one. Now, most homes are they're buying 3 or 4 or 5 of these things, right? So that's the difference. If you want to get off the grid, if you want to be resilient for the next one of these shutdowns, if you have an ultra efficient building, you're going to give Tesla way less money. You're going to need fewer solar panels, which is good because they have embodied energy. Most of the panels are still made in China, where there's very emissions intensive coal-fired power plants and electricity They are trying to change that. But to the extent that you pivot and you have this building that's very resilient, but you minimize the assets that you put into it because you've designed it to be very efficient, then you have less of an upfront impact, right? And so that's what we're really talking about today. So how do we do it? Well, Passive House, it's really 6 very simple things. The first thing is a thou shalt not, which is if we're going to create a thermally efficient building, we can't have what's known as thermal bridging. That would be like a metal conductor, like the cantilever on a second layer concrete patio or porch that went from the exterior to the interior of the building. So that steel would be removing the heat energy from the inside that you're paying the utility good money for and warming the atmosphere basically. So you will not do that in a design for a passive house. Then the 5 things that you do, you have a very accurate piece of software that has the climate and regional specific sun resources and what days are cloudy, what days are sunny. Use that software with local data on daily temperatures so that you come up with a very accurate model to within a couple percent of the energy's consumption on an annual basis. It's been proven on tens of thousands of homes, whether you're somewhere in Japan or Australia or here in Santa Cruz. We have very good climate data that you can put into that software model so that the response, the physical response of the building design with the climate is ensured. There's a handshake. So the design components, we will have this energy consumption on a 12-month basis. Okay, so that's part 1. Part 2 is you have an energy budget that you can't exceed. It's measured 2 ways. 1, the energy the utility would burn to create the electricity or even deliver the natural gas, there's leakage. And then there's the energy that you would measure at the site at your utility meter outside, or gas and electric meter. So you have dual budgets that the software satisfies this limit. So with Passive House, per square meter of conditioned area, it's 120 kilowatt hours per year. In the English system, it's 11.3 kilowatt hours per square foot of heated or conditioned floor area. Okay? So then, 3, 4, and 5, kind of what you'd expect. A lot of insulation. This is sort of like a beer cooler. We have 24 inches of loose cellulose above us in the attic. We have fiberglass and rigid foam beneath on the floor. The wall assembly went from 5 to 10 inches thick. It's an R23 wall assembly, if I'm remembering. So we basically really improved that. Now, the weakest point of any envelope is the windows and doors, and that leads me to the 4th point. Each one of these, even this glass here, there's 3 layers of glass. So there's 2 trapped spaces in which there is a gas. This one actually only has the atmosphere in it, but all of the others have argon between the layers of glass. It's a larger nucleus with a lower kinetic energy. That's the basis of heat. So the transfer in convective transfer is impeded. So the heavier the atomic weight of the gas, the more resistance to heat through the window. Finally, the most difficult and probably the most important, it can lead to 30 to 40% of your heat loss, is air tightness. So basically, this is not quite a submarine, right? But let me show you. You walk through this front door that looks like a historic front door, and it's actually a modern door. And let me show you what's special about it. So I'm going to disengage the safety, and you'll see that there's 3 anchoring points. On the bottom and the top, you'll see there's a taper in the steel. So what's happening, as it anchors the door and the mating hardware here, it's actually, that taper is pulling the door into this elastomeric seal that goes on all 4 sides, right? So if you just press on that, you'll see even on the bottom. So it's sort of like you've seen in a movie what a submarine bulkhead does, right? So you can actually see that here. We're going to close the door, and from this angle, if you stand sort of in front of the gramophone, it's difficult because of the shading, but look at this space here, and you're going to see when I engage that hardware, you see it moved in about a millimeter and a half.
Just to compress that seal.
Right. So basically, this there's many components that kind of look like, well, it looks like an old house. It looks what I've seen every house. But then if you look closer, there's a little difference, a nuance. It's very important. And if you multiply that and make it consistent, it's kind of like the swarming that I was talking about. You have all of these little autonomous groups, and they're all highly focused on the goal, but they're sort of at freedom to approach the problem solving that's suitable for their specific, discrete little area of engagement in the overall purpose, if you will. So if you look at this window, it's kind of behind all this stuff, but it also has double seals, but it's done very differently because it's an awning door, okay? But there's two places. There's a seal here, and there's a seal here. And there's hardware in multiple places that bring that door into the frame, okay? So let's retrace. We've got the highly accurate software with the local climate data. We have the double budgets of energy measured at the utility and at the home. We have extreme amount of insulation. We have very high quality windows and doors, which by the way are the weakest part of what we call the thermal envelope. If we take a thermographic image, that's even this home, that's where we're losing the heat or gaining during a heat wave. And finally, we have the air tightness. So when these things all dance with each other, and they're all on the beat, right? You have an extraordinary radical result, which is that 80% reduction. And again, when I first heard about it, I was like, this can't be. But then as I looked at each building system, and I looked at sort of the random, stupid approach in the past, yes, it is possible. And we did it with this house. You can see, these are the utility bills we actually reduced before and after by 80%. Okay? Now, what's amazing is that there's all these other benefits. During a heat wave or during a cold snap, this building has what's called a very long time constant. So imagine if you had an experimental chamber. And in this experimental chamber, you could indefinitely keep a 1 degree temperature difference between the inside of a structure and the outside. And you had a clock so that you could measure when would the thermal equilibrium occur? How many hours would it take the inside to get exactly the outside temperature? You can measure this. It's called tau, or the time constant of a building. Now, with these public safety power shutdowns, tau is now all of a sudden really important to everyone. Because if we lose power for 2 weeks in the winter, and we're in southeastern Maine, this can be a life-threatening thing, right? So that's why the city of New York, every new municipal building is designed to this passive house standard, because the employees, it's never going to get below the high 50s. As long as they're human beings in here, each one of us is emitting about 100 watts of energy, mostly through radiant transfer, infrared. There's a tiny silver coating on this glass. It's reflecting that infrared back into the house. So it's recycling even the heat of our bodies. The waste heat from the refrigerator, which is simply a heat pump, all of that heat is being recycled, okay? That's why they made that decision in New York City, because critical facilities that lose fuel and electricity for a long period of time, they still need to provide those critical services, right? So we had a 4-day heat wave. We cooled passively at night, but we stayed in the low to mid 70s when it was 100 degrees for 4 days in a row. That's the power of intelligent design, okay? Once you realize this is possible, why would you not do it? And yes, there's an incremental cost, but once you live in a house like this, you're like, what on earth have we been doing? Because we could have figured this out 100, 150 years ago, really. There were triple glazed skylights in Arctic exploration vessels that were, wind powered. These were going up to the Arctic, and they were primarily wind powered masted vessels, and they had triple glazed skylights, right? So there's bits and pieces that we've known for a long time, but we really weren't focused on how do we live lightly and cleverly in our buildings until now. So it's an exciting time because the science is really pivoting quickly. And again, this comes back to this swarming idea. We're sharing this to hope to get you excited, so you'll go out and we'll learn from you in your tour. Because, and as we'll see in some of the other parts, we learned, there was some unexpected learnings, right? So I kind of given you the 5 key points of passive house. The 6th thing, we avoid the thermal bridging, and just a little bit of the history. So very famous in terms of passive house, in 1979, 40 years ago, the Saskatchewan Conservation House was built in the Saskatchewan province of Canada. It was the first building that combined heat recovery ventilation with super insulation. It's still there. It's still working. The Germans and the Chinese studied this house. They looked at some of the key ways that you could make it universal, that you could map it to anyone on the planet, and they came up with a passive house standard, which we have today. So this house, it turns out, a little bit more in the history, is the 1/1,000,000th square meter of certified passive house. There's an institute in Darmstadt, Germany, and they check all of your data, make sure that it meets the engineering standard. But we met that certification. It was difficult, but possible, and it turned out we're the 1/1,000,000th square meter on the planet. So we have that plaque over there.
Yeah, nice.
So this is really growing. And just I'll leave on the history. In China, they've kind of, it's like taking them by storm. They've realized, well, this is really sound science, and we as a country are very constrained with energy, huge issues with pollution. So they're going to be building some of the largest passive house projects. Probably, in 5 years, just the built environment that's passive house in China will exceed the rest of the planet. So they've like taken this in, they've drank the Kool-Aid. It's like, oh, this is good Kool-Aid. I'm gonna do this. So that's the end of part 1. I may have forgotten a few things.
Are there any other houses in Santa Cruz
Yes.
on the passive house end?
There's at least one other structure in the city.
Do
The
I-
city, okay, in the county. There's some other passive house. Yeah.
You mentioned the walls. Are these the original thickness walls of the house? Or
So the
have they
original wall thickness was 5 inches,
been... Okay.
and we'll see it in a slide in one of the studies. What we did was we attached rigid insulation to the exterior framing after we did.
Outside. Oh,
Yes,
okay.
it's
okay.
mineral wool. We put a 3¼ inch thickness mineral wool,
Right.
as well as putting insulation between the wood framing members.
So
the
is that on
studs.
top of the original cladding, or
So the cladding, interesting story. So I studied the architecture of the 1920s because even when this home was built in the 1920s, it was missing some of the key vernacular components of style. Like it didn't have the divided lights in the windows.
right?
It didn't have the flare at the bottom of that framing. It's called battering. And it's a lovely thing. People say, oh, it looks like the Hobbit house, but it actually kept the water away from
Yes.
the footing of
Yes.
the part of the foundation that goes into the soil, right? So it kept that soil less moist. So actually, it looks cool, but also, it form follows function, in other words. So that was added. So there are a lot of little things that we added. It was an interesting project management experience for both of us, because we both had project management experience, because we were trying to do this incredible energy performance, but we also wanted to improve the historical architectural feel and make it look even better than it was when it was built in 1922. This house was built in 1922.